Welcome to the next session of the subject Engineering Maths. We were discussing chapter 3 Calculus. We were in differential calculus, and in this session we continue the concept of maxima and minima of functions of single variable, right? In the last session we have completed 3 to 4 definitions based on maxima and minimum. One point is stationary point, another one is maximum value, minimum value, local maximum and local minimum, right? Now we discuss a procedure to get maximum and minimum values of functions of single variables over the domain set of real numbers. As I mentioned in the last session, we discussed maxima and minimum values of a functions of single variable over two different possible domains. One is set of real numbers and another is set of closed interval a comma b. So when you handle maxima and minima of functions of single variable over the domain real numbers, there is no assurance about its maximum and minimum values. May exist, may not exist. But when you define maxima and minimum values over closed interval a comma b, definitely they exist. Okay. So at first we discuss maxima and minimum values over the domain R. The name of the procedure is second order derivative test. Second order derivative test. Suppose we have a function f of x defined over set of real numbers R. I need to find its maximum and minimum values over the domain R. Now we have 5 steps. Let us discuss one by one. First one is calculate all stationary points of f of x. Calculate all stationary points of f of x and assume that P is one of its stationary points. P is one of its stationary point. So what is step 1? It involves the calculation of all stationary points. How to get stationary points? Find the derivative of f of x and make this equal to 0. You will get some roots and they become stationary points of this function. So assume that P is one of its stationary point. Step 1 is evaluate d square y by dx square at x equal to p. At x equal to p. Actually function is f of x. So generally function values we store in the variable y. So evaluate d square y by dx square at x equal to p. And this factor will decide about p, whether p is a local minimum or p is a local maximum or p can be a local minimum or local maximum. Therefore, this is a deciding factor to say about the value p, because stationary points behave differently in terms of functions. Okay. So my choice is how p can be a local minimum or how p can be a local maximum like this. See, one general example is I always used to mention in the class. If the results were out for students, then a faculty may ask you, teacher may ask you, who is the highest topper of the class? Who is the least topper of the class? So generally, but if a faculty has some opinion about the particular class, generally frequently students may interact with faculty members. Some students may interact very frequently. So whenever faculty observes all these points, they may guess, yes, this particular fellow can be local minimum or this particular fellow can be local maximum, something like that. So in that way, when the results were out directly, they may ask you, are you the topper or are you least topper, something like that. So faculty have some opinions on students. That depends on, for example, the way you are interacting with faculty members, etc. So therefore, here also, what are the typical students, what are the typical points in terms of functions? They are stationary points. So therefore, I am going to calculate the functional values at the stationary points. So I may get more chances whether the stationary points are local minimums or local maximum. Hope you understand this. Okay. So in the step 2, evaluate d square y by dx square at x equal to p. What is my y? Y is my function f of x. Now step 3, if d square y by dx square at x equal to p is less than 0 implies p is a local maximum. Implies p is a local maximum and maximum value equal to f of p. So in this case we were getting two issues. What is local maximum and what is maximum value? So when d square y by dx square at a stationary point is less than 0 implies this point is a local maximum and maximum value equal to f of p. Now step 4. If d square y by dx square at x equal to p is greater than 0 implies p is a local minimum. Local minimum means at this point the function gets minimum and min value equal to f of p. Step 5. We have covered already less than 0, greater than 0. Now we have 0 quantity. That is, if d square y by dx square at x equal to p equal to 0 is 0, then the test fails. Then the second order derivative test fails. What does it mean? See, when you go to point number 3 and point number 4, definitely they give accurate values if the domain is R. When d square y by dx square at a stationary point is less than 0, second order derivative test at a stationary point is less than 0 implies at this point the function gets maximum. That's why I say p is a local maximum. Since p is a local maximum, maximum value equal to f of p. If it is greater than 0, that we have discussed in case 4. If d square y by dx square at the stationary point is positive, at this point the function gets minimum. That is, p is a local minimum. That's why minimum value equal to f of p. Now, if d square y by dx square at x equal to p is 0, then the test fails. It means that we can't conclude directly about p. That means the result may vary from example to example. In certain cases of examples, p can be local minimum. In certain cases, p can be local maximum. In few cases, it can be neither local minimum nor local maximum, and in few cases, it can be both local minimum and local maximum. That varies from example to example. But when you get case 3 and case 4, definitely the results will be like this, accurate results. But when you get case number 5, you can't say. So when you are handling case number 5, we have some different procedures. Okay, so note down these points. Now at this point, please continue. I dictate. If d square y by dx square at x equal to p is 0 implies the test fails. Then the test fails. That is, p can be a local minimum. P can be a local minimum or a local maximum. P can be a local minimum or a local maximum, or both or none. Or both or none. Remember one point, second order derivative test can be applied only when the domain is set of real numbers. If the domain is closed interval a comma b, the procedure slightly may change. Okay, so now let us discuss one simple way to get maximum and minimum values of function if the domain is closed interval a comma b. Suppose we have a function f of x whose domain is closed interval a comma b. Whose domain is closed interval a comma b. I need to discuss its maximum and minimum values of this function over the domain is a comma b. So as usual, you find the stationary points. Find stationary points. Suppose the stationary points are, for example, x comma y. Suppose if x comma y both belong to this, if x comma y both belong to closed interval a comma b, for example, then evaluate four parameters. One is f of a, f of x, f of y, and f of b. Let me explain clearly. I have a function f of x whose domain is a comma b, closed interval. So as usual, you find the stationary points, because stationary points are typical points. They are the deciding factors to get local minimum or local maximum. Okay. So whenever you find the stationary points, immediately you will get one or two or three stationary points. Assume that x and y are my stationary points. Now look at how many stationary points belong to this interval. Suppose if all stationary points belong to this interval, then calculate function value at the endpoints as well as stationary points of that interval only. I will tell you an example also. So whenever x comma y belong to same interval, calculate f of a, function at the starting point, f of b, function at the endpoint, and followed by functional values at the stationary points, f of x and f of y. Now assume that these values are like this. For example, this value is v1, this is v2, and this is v3, and this one is v4. Now among these v1, v2, v3, v4, suppose if v3 is maximum, for example, say. So in that case, this v3 is the maximum value of this function in the entire interval a comma b, and this y I can call it as a local maximum. So in that case, this y will be called as a local maximum. Suppose if this value is minimum among v1, v2, v3, v4, if v1 is minimum, then in that case this v1 is the minimum value of the function f of x in the overall domain a comma b, and in that case this a becomes a local minimum. So what I mean to say is, when you are finding the maximum and minimum values of functions of single variable over the domain closed interval a comma b, local minimum or local maximum occurs either at endpoints or stationary points only. So maxima or minima are possible either at endpoints or stationary points of an interval only. Now I will tell you one general example. Suppose I have a function f of x. Domain is closed interval a comma b. Assume that its stationary points are, for example, 3, 4, 7. This is my function. I need to find its maximum and minimum values over the domain closed interval 2, 5. As usual, you find the stationary points. Assume that the stationary points are 3, 4, 7. Now here 7 is not a member of this interval, so ignore 7. But 3 belongs to this and 4 is a member of this. So calculate f of 2. You must always calculate function value at the endpoint. That is essential factor, compulsory. So f of 2, 3 is a member of this, calculate f of 3. 4 is a member of this, calculate f of 4. 5 is the last boundary point, calculate f of 5. So among these 4 values, whichever is maximum, and that value will be maximum of this function in this interval, and the corresponding point is called local maximum. The same point you can apply for local minimum as well as minimum value. So whenever you are finding maximum and minimum values of functions of single variable over the domain a comma b, maximum or minimum values occurs either at endpoints or stationary points of an interval only. You should not apply second derivative test. When you apply second derivative test, even if the domain is a comma b, you may not get accurate results. I will explain that point during classroom workbook problems, but for the time being, you try to understand this. Okay? Note this point. The maximum and minimum values of functions of single variable. The maximum and minimum values of functions of single variable in closed interval a comma b. The maximum and minimum values of functions of single variable in closed interval a comma b occur either at endpoints or stationary points of an interval only. Occur either at endpoints or stationary points of an interval only. I repeat once again, the maximum and minimum values of functions of single variable in closed interval a comma b occur either at endpoints or stationary points of an interval only. Now with this we have finished how to find maximum and minimum values of single variable over two different domains. One is set of real numbers, second one is closed interval a comma b. Okay. And this is one of the important topic. Frequently they were asking questions in GATE and even in IES also. Now let us discuss classroom workbook. Based on the concept maxima and minima. Based on the concept maxima and minima. Just all of you open classroom workbook. Now let us start classroom workbook from question number 26. Question number 26. What it is? For all real values of x, the minimum value of the function f of x equal to e power x plus e power minus x occurs at, or they were asking directly the minimum value of this function for all real values of x. So x is a real number. So they were asking the minimum value of this function is. So that means what is the domain? The domain is set of real numbers. Options are given 2, 1, 0.5, 0. We need to find its minimum value over the domain is R. So since the domain is R, you need to find stationary points. Even if the domain is a comma b or set of real numbers, stationary points must be evaluated. That is compulsory factor. So stationary points must be obtained like this. F dash of x equal to 0. So its derivative is e power x minus e power minus x is 0. Therefore e power x equal to e power minus x. Therefore x equal to minus x. Because base values are equal, powers must be equal. This implies 2x equal to 0. Therefore x equal to 0 is a stationary point. Now let us calculate second derivative, that is f double dash x. So this is given by e power x plus e power minus x. Now replace x by the stationary point. F double dash of 0 equal to e power 0 plus e power minus 0. This is 2 and this is greater than 0. So here the second derivative test at a stationary point is becoming positive value. Therefore this point is a local minimum. Therefore 0 is a local minimum. 0 is a local minimum. Therefore its min value equal to f of 0. Min value equal to f of 0. This is e power 0 plus e power minus 0. This is 2. So option A is right answer. But be careful about this question. Generally minimum value is different from local minimum. Here at the point 0 we were getting minimum value. So that's why 0 is a local minimum. But unfortunately in options one of the result is 0. So don't confuse with this. 0 is a local minimum. So minimum value is f of 0. Okay. So answer is A. Let's go through question number 27. Consider the function f of x equal to x square minus 4 whole square, where x is a real number. Then the function has option A, only one minimum, only two minima, three minima and three maxima. So that means actually whenever function is given, you assume that the function is equivalent to classroom, a particular class. So they were asking this particular class has only one minimum, that means one least topper, only two least toppers, three least toppers, three highest toppers. Always function will be equivalent to classroom. So the question is related to how many least toppers were there in the class. So options are given like this: one topper, one least topper. Okay, so two least toppers, three least toppers, and one option is given to highest topper, three highest toppers. Now, how to handle this? Here x is a real number, so we can apply second derivative test. Now let us try to handle in a different way. Here the function is x square minus whole square. This is even power. So because of this even power, this function is, that is x square minus 4 whole square, is always greater than or equal to 0. Will you accept this? X square minus 4 whole square is greater than or equal to 0 because of this even number. Therefore, its the least value is 0. So min value of f of x is 0. And 0 is possible at two different points. And 0 is possible at 2 points. One is 2 and another is minus 2. Because when you replace x by 2, 2 square minus 4, that is 0. When you replace x by minus 2 whole square minus 4, again 0. Therefore, its minimum value is 0 and we were getting 0 at two different points, 2 and minus 2. Therefore, this function has two local minimums. So, therefore, that means only two minima. Only two minima. So therefore this is option B is right answer. Or you can handle this by using stationary points. Evaluate stationary points, you will get 2 and minus 2, apply second derivative test, definitely you will get 2 and minus 2 or local minimums. Okay, understand this? Here because of this even power, this value is always non-negative. So it is greater than or equal to 0. That means its least value is 0. So that is minimum value of this function is 0 and 0 is possible at 2 points, 2 and minus 2. Replace x by 2, this value is 0. Replace x by minus 2, it is 0. Therefore, the function is taking a minimum value at two different points. So therefore, the option is only two minima. Let's go through question number 28. Consider the function f of x equal to x square minus x minus 2. The maximum value of f of x in closed interval minus 4 comma 4. Its maximum value in the closed interval minus 4 comma 4. Options are given like this: 18, 10, minus 2.25, indeterminate. So indeterminate is not possible because when you try to find maximum or minimum values in the domain a comma b, certainly they exist. So option D is wrong. Now let us try to find its maximum value. So at first find the stationary points. F dash of x equal to 0. This implies 2x minus 1 equal to 0. Therefore x equal to 1 by 2. This is a stationary point. Fortunately, this 1 by 2 belongs to this interval. So this belongs to closed interval minus 4 comma 4. So you must consider this point. Now calculate function at these two endpoints as well as stationary point of this interval. Calculate function value at these two endpoints as well as stationary point of this interval. So f of minus 4. Replace x by minus 4. Minus 4 whole square minus of minus 4 minus 2. So this is 16 plus 4 minus 2. This is 18. F of minus 4 is 18. Now calculate f of 1 by 2. This is 1 by 2 whole square minus 1 by 2 minus 2. So therefore 1 by 4 minus this one is 2 minus 1 by 2. 1 by 2 minus 2. So here the LCM is 4. This is 1 minus 2 and this one is, say for example, this is 8. So therefore minus 9 by 4. So this is minus 2.25. Now calculate function at the last point f of 4. So this is 4 square minus 4 minus 2. So this is 16 minus 6, this is 10. Now you can see minus 9.25 is in one of the option. 10 is one of the option. Even 18 is one of the options. So when you are handling questions like this, be careful. So 18 minus 2.25, 10, everything belongs to options. But among these three, 18 minus 2.25, 10, this is the maximum value. Therefore, the maximum value of this function is 18. Therefore, option A is right answer. To question number 29. The maximum value of f of x equal to x cube minus 9x square plus 24x plus 5 in closed interval 1 comma 6. In closed interval 1 comma 6. Options are like this: 21, 25, 41 and 46. Let us see its maximum value if the domain is closed interval 1 comma 6. Now as usual, find the stationary points. Stationary points are obtained by finding the roots of f dash of x equal to 0. So the derivative of this 3x square minus 18x plus 24 equal to 0. You can take 3 common. So x square minus 6x plus 8 equal to 0. Its factorization is x minus 2 into x minus 4 equal to 0. Therefore, the stationary points are 2, 4. These are my stationary points. And both stationary points belong to this interval. So, both belongs to closed interval 1, 6. Now, calculate function value at the endpoints as well as stationary points of this interval only. So, let us calculate f of 1. When you calculate f of 1, so the result is 1 minus 9 plus 24 plus 5. So this is 24 by 1 minus 9 plus 24 plus this. So 30 minus 9, this is 21. F of 1 is 21. Now calculate f of 2. F of 2 equal to 2 cube minus 9 into 2 whole square plus 24 into 2 plus 5. So this is 8, 9 4 36 plus 48 plus 5. So therefore this is 48 plus 5, 53, 53 plus this 61 minus 36 and this one is 25. Even 25 is one of the option. 21 is one of the option. Try to observe options. Next, to calculate f of 4. F of 4, replace x by 4. 4 cube minus 9 into 4 square plus 24 into 4 plus 5. So therefore this is 4 cube is 64. This is 16 nines is 54. This is 144. So 16 nines are 144 plus 24 fours 96 plus 5. So this is 96 plus 400 160. So this is 165 minus 144. Again this value is 21. Of course we got 21 at two different points, 1 and 4. Now calculate f of 6. F of 6, replace x by 6. This is 6 cube minus 9 into 6 square plus 24 into 6 plus 5. 6 cube is 216 minus 36 nines. 36 nines. 6 nines are 54. 3 nines 27 plus 5. 324. So therefore this is 324. 24 sixes. 220 into 6 120 plus this is 144 plus 5. So therefore this is 216 plus 149. So this is 15. This is 6 3. So therefore this is 365 minus 324. So therefore this value is 41. This value is 41. Now when you look at all the values, at 1 we got 21. So at 1, at 2, 25. At 4, this is again 25. At the last point, we were getting 41. Now, among these values, 21, 25, 21, 41, 41 is maximum value. Therefore, the maximum value of this function is 41. Option C is right answer. So, option C is right answer. Now, let me tell you one point in this case. When you try to apply second derivative test, what happens? Let us see. I will try to apply second derivative test. Second derivative test. What is f double dash of x? This is f of x. F double dash of x equal to 6x minus 18. Now replace x by the stationary point 2. So f double dash of 2 is 12 minus 18 minus 6. It seems to be negative. When a second derivative at a stationary point is negative, implies 2 is a local maximum. Therefore, maximum value equal to f of 2. But what is f of 2? Already we got it. This is 25. So we got maximum value is 25. But this is a wrong choice because 25 is not maximum, because there is another value in the same function which dominates this 25. Therefore, 25 maximum value is 25. This is absolutely wrong statement. Therefore, these are the conflicts when you apply second derivative test if the domain is closed interval a comma b. Sometimes you may get accurate results, but in most of the cases you don't expect accurate results by applying second derivative test if the domain is a comma b. Hope you understand. So you can make this comment, but this is a wrong statement. So you cannot apply second derivative test if the domain is closed interval a comma b. This is the pitfall of second derivative test if the domain is closed interval a comma b. Okay, note this. Now let us move to question number 30. A political party orders an arch for the entrance to the ground in which the annual convention is being held. The profile of the arch follows the equation y equal to 2x minus 0.1 into x square. Let me write out the equation. Y equal to 2x minus 0.1 into x square. What is y? Height of the arch in meters. Y is height of the arch in meters. So the maximum possible height of the arch is. So what they ask indirectly, they were asking the maximum value of this variable y. So answers are given in terms of meters. Now let us see. So here y is a function of variable x. Let us calculate stationary points by taking dy by dx equal to 0. Make derivative equal to 0, you will get the stationary points. So this is a 2 minus 0.2 x equal to 0. This implies x equal to 10. So 10 is a stationary point. What is the domain of this function? Here interval is not given. So the domain is set of real numbers only. Calculate d square y by dx square. I am going to apply second derivative test. This becomes minus 0.2. Therefore, d square y by dx square at the stationary point 10 equal to minus 0.2 only. This is a negative expression. So second derivative at a stationary point is less than 0. Implies, what do you say about this 10? This is a local maximum. Therefore, 10 is a local maximum. Therefore, what is my maximum value? F of 10. Maximum value equal to f of 10. Now replace x by 10. 2 into 10 minus 0.1 into 10 whole square. So therefore this is 20 minus 0.1 into 100. So this is 20 minus 10. This is again 10. So interestingly, maximum value is 10 and even local maximum is 10. So don't confuse. Sometimes it may happen. Local maximum is 10 and even maximum value is 10. So therefore the maximum possible height of the arch is 10 meters. So option B is right answer.